Hey everyone, I'm Anish and welcome to PrepFusion. So today we will be starting the lecture 2 of frequency domain analysis, right? So in the previous lecture, we learned like what is the meaning of frequency response, right? What is the meaning of steady state sinusoidal response? There we understood that we'll get two terms, right? One is the AC transient and one is the steady state sinusoid response. The AC transient, if my system is stable, it will die down, and the sinusoid steady state response will remain. And that response, right, will be related with my system and the input frequency, right? All those things we proved in the previous lecture. So I hope you are able to understand why do we call it sinusoidal steady state response, because we're talking about the steady state and not the like the transient part, right? And also like my output, right, isn't like settling to some value because my input itself is a oscillatory nature, right? The input itself is in oscillatory nature, hence my output will also be oscillatory in nature. Even though my system is stable, but my input is oscillatory, hence my output will also be oscillatory. In time domain, what we did, we gave some unit step, right, and it was settling right to 1 at steady state. So like my output also was settling to some value, but obviously after some transient part, right? So all those things we measure, right, in time domain analysis. So I hope you got a brief idea about frequency domain analysis, right? Now in this lecture, what we'll study? We'll study about the polar plot. What is a polar plot, right? So as I gave you a brief overview, that polar plot is basically plotted for all the positive frequency, right? And it is plotted with respect to two axes. One is the imaginary of g of j omega, h of j omega, and real part of g of j omega and h of j omega. Basically j omega means, like, when we put s equals to j omega, by that we mean we are finding the frequency response, right? Frequency response. Okay, so like in the transfer function, if you put s equals to j omega, then that is known as the frequency response of the system, right? Frequency response of the system, as we did in the previous example also, right? There, right, here what did we prove? Like this, right? We put s equals to j omega here, right? J omega naught, whatever was the frequency, omega naught, whatever was the frequency, like that's why this j omega terms comes, right? So I hope, like, if you go through the proof, you will understand how does this j omega term comes, right? Okay, so yeah, this is this one. Okay, so now, like, we put s equal to j omega and like we plot the OLTF, not the transfer function here, right? We plotted the closed loops. This is the CLTF, right? T of j omega is the CLTF, but here, right, we plotted the OLTF. Okay, so what is, like, why do we plot the OLTF and what are the different parameters of OLTF? All those things we'll understand slowly, but for now you just understand or you just try to understand that polar plot is a plot of imaginary part of g of j omega, like OLTF, and the real part of OLTF, right? So this is the real axis and this is the imaginary axis. Just like in complex numbers, this is the real number plane and this is the imaginary number plane. Okay, now, like, let's read this. Polar plot is a combination of absolute values of magnitude and phase angles in degrees. Okay, so even though if you don't understand, that's okay. Basically it is telling me about the absolute values, right? So even though if you don't understand, that is fine. Okay, versus the omega. So what will vary here? Will vary the omega here, right? We'll see the variation of the imaginary part and my real part with respect to my omega. So here, right, my x is real of g of j omega. So let me write my x, right? X is this one, real of imaginary of j omega, x coordinate. Just this simple is just a xy coordinate. And what is my y? Y is imaginary part of g of j omega. And what am I varying here, right? I'm varying another variable, right? I'm seeing the okay, this whole thing got copied. This is that. Again, right? Okay, no. So like what I am seeing is, I'm seeing the variation of this x and y with respect to omega, right? All these are function of omega. So I'm seeing, like, if I vary my input, right? If I vary the input frequency, then how will this plot look like? And this will give us information about the stability and all those things. Slowly we'll understand it. So yeah, like all for all real positive values of omega. Okay, so these are my xy coordinates, and this is basically the graph that where we will plot. Okay, and few more things, like this is just like the locus diagram, right? If you would have until now, if you have finished the network theory, right? In network theory there is one chapter, locus diagram, and exactly that is what we did, right? We varied one parameter, right? One parameter was the variable, and we plotted the other parameters with respect to that variation, right? And that is what basically locus diagram is. So this is also like a locus diagram. Like in root locus, what we did, we varied the k parameter, right? K parameter, and we plotted in the sigma plus j omega plane. Basically we plotted the closed loop poles, right? Closed loop poles. Okay, with the variation of k parameter. Exactly here also we're doing the same thing. Okay, don't worry. So another thing is that let us, like, although I have already revised to the angles, let us again revise the angles, right? So tell me, what is this angle? Like this angle, what is this angle? This angle is 0 degree, right? This angle is 0 degree. Okay, this angle is 0 degree. Now tell me, what is this angle? If I go from here, this positive x-axis to here, right? How much clockwise or anti-clockwise did I move, right? Or what is the amount of angle did I move? So the amount of angle will be simply plus 90, right? Plus 90 degree, because I'm going in the anti-clockwise direction. Okay, if I'm going in the anti-clockwise direction, then obviously my angle will be positive. Okay, and as I'm moving total of 90 degrees, it will be plus 90. Now tell me, what is the angle at this point? Okay, if I move again another like half, right, then what is the angle? Tell me. It is 180, right? Another plus 90 I move, so 90 plus 90, it is 180. Now again, if I move another 90, again this will be 270, right? And again, if I move another 90, this will be 360. Like this 0, right? You can add 0 or 360. Okay, just to get your basics clear, right? This will be required in the next few like hours or lectures, right? So yeah, this is this one. So now, right, now what we need to do is basically, just wait a second, let me see if it is recording or not. Yeah, it is recording, fine. So like what I was telling was that now let's move in the negative direction. Okay, let's move in the negative direction. So again, if I'm at 0 degree, if I want to move in the clockwise direction in at this point, okay, at this point, then how much did I move? I moved 90 degrees, that is correct, but I moved minus 90 degrees because I'm moving in the clockwise direction, not in the anti-clockwise direction. So this will be minus 90 degrees, right? This will be minus 90 degrees as I move from here to here, right? Move from here to here. Okay, again, if I move another like half, right, another quarter basically, so how much did I move again? I moved again, right, minus 90 degrees. So again, right, this will be minus 180 because minus 90 I already moved, and again another minus 90 I moved, so it became minus 90. Again, if I move another 90, right, it will be minus 270. So I'm trying to explain you like both the positive and negative angles. Generally what happens is you really get confused with the negative angles. So if you are going to clockwise, then it will be negative. If you are going from anti-clockwise, then it will be positive, right? So again, right, if I again move 90, this will be minus 360, right? Minus 360. Okay, so like you add 360, subtract 360, you will come back to the same place again because it is a total circle, right? Total circle. 360 is total circle, so you come back to the same place again. So you add, subtract 360, it doesn't matter. So these are few things to keep in mind, basically angle. And like here, right, so here we will plot for all positive values of omega. Why this is important? Because in the Nyquist plot, when we will study the Nyquist plot, there we will plot for negative values of omega as well. Okay, so that's why polar plot is only for positive values of omega. Okay, 0 to infinity. Okay, so yeah, this is what my like basic definition of the polar plot is. So let's read these few points of a polar plot. In polar plot, positive angle is measured in the counterclockwise direction, already explained, right, from the real axis. Okay, for at a given value omega. Okay, at any given value omega, positive angle will be in the anti-clockwise direction or counterclockwise direction. And the instantaneous magnitude of the OLTF is represented by the instantaneous value of the distance from the origin to the point at a given point. So origin, this is the origin, and let's say for a particular omega, my x and y lie here, right? X and y coordinates are here. So if I draw the vector or distance, measure the distance from the origin, draw a straight line from the origin to this point, the distance of this point will be the magnitude of my OLTF. Like how does this happen? Basic Pythagoras theorem, right? So this is the let's say this is the x coordinate, this is the y coordinate, right? And this is a right angle triangle. So if I do x square plus y square, I get this one, right? And what is x square? X square is real part of g of j omega OLTF, and y is imaginary part of OLTF. So if I do real part square plus imaginary part square, I get the whole magnitude itself, right, of the OLTF. So basically that is what this is telling, right? So yeah, this is the magnitude. So I hope you got the idea. And polar plot also describes the stability of CLTF by using frequency response of OLTF. How we'll understand, but these are few points to keep in mind. This I explained to you, and how we'll understand the stability of CLTF by only using the OLTF, we'll understand, because this is very interesting, right? We sometimes what happens is don't want to find the like CLTF and stuff, just want to see how does the variation in OLTF vary the stability, right? So generally we want to vary the OLTF itself. Okay, that's why this is very we want to do this. We want to do find the stability like from OLTF. Else you can say, sir, we can just simply find the CLTF itself, and from there we can find the stability. Yes, but generally what happens is in a system, right? In a system, we vary the OLTF itself and not the CLTF, right? Because like generally what we do is we use the negative unity feedback system, and in negative unity feedback system only we have OLTF. So by varying the OLTF, how are my CLTF changing, or how is the stability of the system changing? That is important. Okay, that's why we're really interested in the stability of my system with the help of my OLTF, like analysis of that one, right? So yeah, these are few points. Now let's straight away get to our polar plot, right? Basically we have to draw the polar plot of the following OLTF, right? We have to draw the polar plot of the following OLTF. So you try to pause the video, right? You try to pause the video and you do all these examples. So what do you need to do? You need to separate out, right? You need to separate the imaginary part of j omega or real part of j omega, and then plot, right? uh, these are the OLTFs. Or what you can do, you can find the angle and the magnitude, like that also you can plot. How? As I explained, right? Let's say my x and y coordinates are here, right? My x and y coordinates are here. So what I just told you, this is the magnitude, and what is the angle? Angle is from here, right? As I mentioned in the first point itself. So we can plot this using two ways, either using the angle magnitude method or using the real and imaginary part method. So I will in the first example, right, I will try to do it using both methods, and after that we'll only use the uh, magnitude and the angle method. Okay, why we'll see. So you try to solve it by yourself. So this is the, okay, let me use another. Okay, so this is g of s into h of s, right? So what is g of s into h of s? It is 1 over s. It is 1 over s. Now let's convert this into frequency response. So I'm just giving a sinusoid input this time. So what I will do, I will put s equals to j omega, right? So as I'm giving only sinusoid input, one by j omega. Okay, so this is what my sinusoid input is. Now let's do it using that method. So here, right, what is the imaginary component? So the imaginary component, okay, like if I further rewrite it, so I will do it with method 1. Real and imaginary component. So basically, right, so like if you find the real component, so I will further like rewrite this one. So what you can do is, this is equals to minus j, like if j goes above, or what you can do, you multiply j both in the numerator and denominator, you will see, you will get this one, right? So j square will be minus 1 and this will be minus j by omega, right? So what is my real component? Okay, I can further write this one as 0 plus this one, right, which is equals to 0 plus j into minus 1 over omega. Okay, so I can write it like this one. So from here I can write my imaginary component, my real component, real of this, right, real of this one is 0 itself. I don't have any real component. Okay, it will always lie on the imaginary axis itself, right? 0. And what about my imaginary component? My imaginary component is simply equals to minus 1 over omega. So imaginary component is negative, and it is always like lying on the, like, sorry, it is in the imaginary component itself, and I don't have any real component. So how will my plot look like? So if you understand, you just take few points, right? Okay, let me copy this graph itself. Can I copy this graph? Okay, so this is real of g of j omega, which is 0, so it will never lie here, right? Okay, let me copy this from here itself. So like imaginary component is always negative and real is 0. So I'm not lying here, I'm always lying in this axis, right? And it is always negative. So if I put like, let's say omega equals to 1, omega equals to 1 is here only, let's say minus 1, right? It becomes minus 1. So this is 1 point. Then if I put omega equals to 0.5, I get minus 2. And if I put omega equals to 2, I get 0.5. And this is covering this whole negative axis basically. If I put omega equals to 0, what happens? If I put omega equals to 0, it becomes infinity, right? It becomes infinity. And if I put omega equals to infinity, okay, it becomes 0 itself, okay, very high. So my graph, right, my plot, polar plot will look something like this, right? So like it will start off from infinity, right? Omega equals to 0, it will start off from infinity, okay, then it will end to here, right, into here. Now can you tell me why is this happening like this one? So from here, right, you can understand, if I put omega equals 0, okay, this imaginary component is very high, okay, and what is the angle? Angle is always minus 90 degree, okay. That procedure we'll do in the next like method basically, okay, that we'll understand. But imaginary component is very high. Now if I put omega equals to infinity, what happens? The imaginary component also vanishes. Real component isn't there anyways, but the imaginary component also gets vanished to 0, right? So if it is 0, then I will be at the origin. So 0 comma 0, xy is 0 comma 0, okay, that's why it is like this one, okay. Now let's solve it using the method 2. Magnitude and angle method, right? So what is the magnitude and angle method? So basically I will find the magnitude of g of j omega and the angle, and accordingly I will plot that, right? So you can also plot it like this one also. So my g of j omega is this one, okay. So what is my magnitude? One by omega basically. So my magnitude is 1 by omega, right? So like you can also understand it by this one here, that my imaginary component is 0, okay, 0 square plus omega square, which is equals to 1 by omega itself, right? 1 by omega itself. So you can understand it like this one also. Now what is my angle basically? So my angle, right, my angle is basically like, numerator I have nothing, right? Numerator I have only 1. What is the angle of 1? What is the angle of 1? 1 is a point that is lying over here, okay. Imaginary component is 0 itself. So 0 by 1 is tan inverse 0, which is 0, okay. And this is in the denominator, right? So this will come in with negative sign, okay, minus tan inverse omega, like what was the angle formula? It is y over x. I will not explain it further, right? We have already done this. So it is y over x. So y is like imaginary component is this omega, and what is the real component? It is 0. So it is omega over 0, okay. So this is equals to minus 90 itself, minus 90 itself. So from here itself I can understand my angle isn't a function of omega itself, right? My magnitude is a function of omega, but my angle isn't, right? So my angle is always 90 degrees, minus 90 degrees, hence it will always lie in this region, right, in this axis basically, in the negative imaginary axis. So always in the imaginary axis basically. Okay, so this is this one. So like what in this method what I do is generally we make a table, right? Make a table and plot like write few values of omega, relevant values of omega, and then we find the magnitude and the angle, and then we plot it. Like we approximate the plot. Obviously you can't plot it perfectly, right? Because what is the issue? The issue is we don't have computers, and like you can't plot it perfectly, but we will try to understand few things. From there we can simply approximate our plot. Slowly we will solve question, and from there you will understand, right? So generally what are the 2 points that we pick, right? So like 2 points, these are fixed, these you have to pick anyways. In between you have to also pick points depending on the OLTF, right? So omega equals to 0 and omega equals to infinity, these 2 points we have to pick, right? These 2 points we have to pick. Now what is the magnitude for omega equals to 0? For omega equals to 0, if I put omega equals to 0, this becomes infinity. So this is infinity itself. This is infinity itself. Now like this angle won't change, right? This angle isn't a function of omega, so I will anyways write it 90 over here. Okay, minus 90. And what is like the value of magnitude at omega equals to infinity? At omega equals to infinity I get 0, right? I get 0. And what is the angle? It is minus 90, right? Minus 90. So this is minus 90, it will always remain minus 90, this will be 0. Okay, so it is going from infinity to 0 in the same axis, minus 90, right? So the plot will look something like this. That we already know this one, right? So it will be something like this. Okay, it will go from this point is omega equals to 0, and this point is omega equals to infinity. Okay, and the angle is always minus 90 here, right? Angle is always minus 90. So yeah, this was rather simple, right? Very simple. So like let's do few other problems here, you will understand. Okay, so in the next examples I will only do the okay, I will try to do it in both methods for the next problem only, and after that we will do using the one method. Why? Because that method, right, may take bit more time. This method 1, right, real and imaginary component, may take bit more time. So I will do this one with real and imaginary component, and in the next methods I will do with only method 2 itself, with the magnitude and phase condition, right? So I have this transfer function or OLTF basically. Let me take another page. So if I have this OLTF, right, then what do we do? Again, right, I put s equals to j omega, right? So this is g of j omega, h of j omega, j omega tau, right? 1 plus j omega tau, right? So now what is the magnitude? So I won't do it like that one. I will do it with the method 1 itself. Okay, let me copy this one. So what I will do is I will do like the complex conjugate multiplication, right? Rationalization if you call it. So what I will do, like I have to make this denominator real, and I have to separate this one with real and imaginary components. That's why I will make this one real, and here in the numerator I will get real and imaginary components. Let's see, right? So what I will do, multiply with complex conjugate basically. So this becomes 1 square and this becomes omega tau square, right? Okay, so I'm just skipping few steps here. Now I can simply separate this one out, right? So if I simply separate this one out, what can I write? I can write here 1 by minus j. I will write plus j here, and minus I will take inside, minus omega tau divided by 1 plus omega tau square. Okay, and this is Okay, this is fine, right? This is fine. So this is my real component and this is my imaginary component, simply separated out. What I can see is if my omega is always positive, right, my imaginary component is always negative, so it will lie somewhere around here only. Imaginary component is always negative, so it will lie in this region. It can't lie in this region, right? And my real component, what about my real component? Real component is always positive, right? Real component is always positive. So my x is always positive, so it will lie in this right hand side, and my y is always negative, so it will lie in this quadrant itself. So from here, right, you can find an estimate of where my x and y coordinates will lie, right? So this is just a locus diagram, right? So if you have studied network, you will understand. My x omega is from 0 to infinity. Okay, omega is from 0 to infinity. So my x and y is always positive, right? So now what do you do now, right? So can we plot this one? So I will lie here only, right? I will lie in this location only. But what is the equation looking like? Okay, so if I try to prove it, it will be like very time consuming. Basically it will look like a circle or a circle itself, but it is not exactly a circle, right? It is not exactly a circle if you see. Okay, and like what will happen is, let's say at omega equals to 0, what is my value? My real component is this one only, 1, right? Real component is this one. And at omega goes to infinity, what is happening? My real component is this one. It is basically 0 itself, because this is omega square and this becomes 0 itself, or this also becomes 0. So at omega equals to 0, my real component is 1 and my imaginary component is 0. Okay, and at omega equals to infinity, my real component is 0, my imaginary component is also 0, right? My imaginary component is also 0. So basically it goes to origin at omega goes to infinity, and in between obviously it will lie in this quadrant only, right? In this quadrant it will only lie, right? So like obviously I can't like let me, if I have that, obviously we can exactly plot the value, but this is just the approximation that I can tell you. Okay, let me copy first this graph, right? So let me first copy this graph, and like how it will look like. So at omega equals to 0, it will start from here. This is the 1 comma 0 point, right? Real part is 1 and imagined part is 0. Okay, then it can't go here, right? It will always lie in this region. So it will go something like this one, and towards the ending it will go towards the origin itself, right? Towards the origin itself. Okay, now the shape, right? Shape I can't confirm exactly, but the shape, like exact shape I can do, but I can do approximation. It will be something like this. Okay, and this is the point of 0 comma 0, right? Okay, so when we'll use the other method, there also we'll understand it better, because there, right, we can simply visualize the angle also. Here also you can do like the imaginary component. What you can say is, initially the real component is always reducing. Real component is always reducing, right? Omega, as omega goes up, real component always reduces, so it will only go left, right? It will only go left. That we surely know. Okay, now what is happening to my imaginary component? So what you can say is, if you say my omega tau is really small, right? For smaller values of omega tau square will be even smaller. 0.1 square is 0.01, right? So this will be even smaller. So compared to 1, I can ignore this one. Okay, so if I ignore this one, what do I see? Okay, let me write this one. Component is always reducing. Okay, like the real component is always reducing. Now what about my imaginary component, right? So imaginary component there are two parts. If omega is small, right? So just during the starting phase, if omega is small, what is happening? If omega is small, what I can do is 1 plus omega tau square, right? Omega tau square. I can simply ignore this 1 and I can simply write this as 1. So this gets converted into omega tau itself, okay? Omega tau. Even though it's negative, that is fine. But slowly omega is increasing, so this will also increase. So my imaginary component will increase, right? Imaginary component increase. Now, okay, let me do this in different color. Okay. Now, what about the part 2 basically? If my omega tau is very high, okay, omega tau is very high. If my omega tau is very high, what does this mean? This means I can ignore the 1 this time, right? I can ignore the 1 this time. So this will be omega tau square itself. So what will happen is that my imaginary component, let me write the imaginary component here, there you will understand it better. So in the previous case also. So what will my imaginary component be? It will be minus omega tau, right? Minus omega tau. So it will increase in the negative direction basically. Okay. So this is what my imaginary component is. Now in the first case, in the second case, what is my imaginary component? Like my imaginary component is omega, like in the numerator I have minus omega tau, and denominator what do I have? I have omega tau square. So 1 omega tau will get cancelled. I will be left with minus 1 by omega tau, right? Minus 1 by omega tau, right? So now if I increase omega, what will happen? My imaginary component will reduce. My imaginary component will reduce basically. Okay. So yeah, this is what about my real and imaginary component. So the plot will look something like this. I hope you got it right. The plot will look something like this. Let me make this one better. So initially for very small values of omega, my imaginary component will increase. Then for large values of omega, it will decrease again, right? So it will look something like this. Okay. So from here also you can understand, right? From here also you can understand. So yeah, this is this one. This is imaginary and this is real. So yeah, now right, we'll use the method 2 basically. Let's do the method 2. So what is the method 2? I'll copy this one again. I'll just simply copy this one because it will take too much time, right? Method 2 uses the magnitude and the angle method. So here, right, what is my g of j omega? It was simply 1 plus s tau, right? So it was, if I can write here, 1 by 1 plus j omega tau. Okay, 1 by 1 plus j omega tau, right? Now what is basically magnitude, right? My magnitude is simply 1 square. This time it is changed 1 square into omega tau square. So this, right, this is magnitude itself. I can further simplify it, right? So this is my magnitude itself. What is my angle? Like numerator has 1, right? If numerator has 1, then it is 0 degree. And if what is the denominator? Denominator, right, this time it has a real component. Previously it didn't have a real component, right? So this will get changed to not to tan plus omega by 0. Okay, this will get changed to, this won't be always 90 degree this time. This will vary with omega. Okay, this will be omega tau by 1 itself. Okay, so this becomes minus tan inverse omega tau, right? So this becomes minus tan inverse omega tau. So this time, right, my angle is varying with omega. My angle will change with omega. This time it won't stay in the same axis or something. Okay, so this is the point to note here, right? So but what is one point we can safely say is omega is always positive, right? Omega is always positive, so my angle will always be negative. Okay. Okay, so my angle is always negative. So this one is this one. Now let's draw the table, right? With the table we can easily approximate our plot. So what I will do is this time, right, I will take 3 points. Okay, sometimes you have to take it like that, and the third point that you take, right, it should be simpler to calculate, right? The phase and the angle, sorry, the magnitude and the angle should be simpler to calculate. So here, right, what I can see is, if I take, right, if I take omega equals to 1 by tau, then my real and imaginary component will become 1 plus j1. So I will take that one as my third point. So omega, I will take 1 point as 0, then from 0 I will go to 1 by tau, then from 1 by tau I will go to infinity. Okay, to further approximate it in a better manner, right? So what is like my magnitude at omega equals to 0? If I put omega equals to 0 here, this is 1 by 1 square, which is 1 itself. And what is my angle of g of j omega? What is my angle of g of j omega? It is simply minus tan inverse omega. So if I put tan inverse 0, it becomes 0 itself. So minus 0 and plus 0 are same thing. So it is 0 itself, right? Let me take 0. Okay. Now what is my magnitude at 1 over tau basically? So if I put 1 over tau here, this becomes 1. 1 square plus 1 is 1 square plus 1 square is 2, and 1 by under root 2. Like that is the magnitude. So what is 1 by under root 2? It is basically 0.707. Okay, these things you should like remember, right? These are very like used. So 0.707. And what is my angle? Basically angle will be minus 45 basically. So basically if I put like omega equals to 1 by tau, so it becomes tan inverse 1, which is 45 itself. It becomes minus 45. Minus 45, right? And what about my infinity? So at infinity what is happening? This is going to 0, this is going to 0, and at infinity this is going to like tan inverse infinity. What is tan inverse infinity? It is 90, so it is minus 90 itself. So like the magnitude is going to 0, and this is minus 90 itself, right? Okay, this is minus 90 itself. So this is basically what my table looks like. Now from here we can get a brief idea. So slowly it is starting from 1, right, at 0 degree angle, from the, and on the real axis it is starting positive real axis, then it is going to minus 45, right? The magnitude reduces, right? Magnitude is reducing, and here the magnitude is going to 0 itself, right? So distance from the origin is going to 0, distance from the origin is reducing. Okay, so yeah, let's now plot it basically. So basically, right, it is starting on the real axis, okay, then like it is starting at 1 comma 0, right? So this is at omega equals to 0. Okay, then slowly what is happening, it is going towards negative, right? And the magnitude is also reducing. Like here initially the magnitude was this, now the magnitude will reduce a bit, and then it will go towards 0. So it will look something like this. Okay, so like this will be like a circle only, semicircle only, right? So and like this will be center, basically you can say half and minus of 1 by tau will be the same, like at omega equals to 1 by tau we will get a center, right? So yeah, that is this one, and this is omega equals to infinity, and this is omega equals to 0, and like this point, right, this point the magnitude here is like if I zoom in further, it is 0.707, and the angle, right, angle is minus 45 degrees. Do remember, right? Minus 45 degrees. Okay, this is my angle and magnitude basically. Okay, so yeah, these are my plots basically. So like let's do the third plot also. What was my third plot? So this time, right, now I will do it using like the first method. I will only use it using the second method itself. So if I copy this one, okay, again I will have to replace s with j omega. Okay, so yeah, this one is this one. So now what you will do, simply do the magnitude and angle calculation, which will be much faster, right? So this time I will straight away go to the magnitude and angle calculation. So what will my magnitude equals to? Just magnitude of g omega into h of j omega equals to, like, this will, I'll just do it bit fast now. So I was doing it slow, now I will do it fast. So this will be 1 like omega itself, and this will be minus like under root 1 plus omega square, right? Omega tau square. Okay, so this is this one, right? So now what is my angle? What is my angle? So angle, right? Angle of g of is basically 0, and these are in the denominator, right? So this will contribute how much angle? This will contribute 90, right? 90, but it is in the denominator. I will write it in brackets. This will contribute 90 plus 90, and how much will this contribute? This will contribute tan inverse omega tau, right? So doing it with fast right now. This is basically tan inverse omega tau by 1 basically, and this has real component 0, hence it is totally contributing 90 degrees. So yeah, this one is this one. Now further, how can I simplify this one? This will be minus 90 minus tan inverse omega tau by 1. So not by 1, omega tau itself. So what can I say about this angle, right? So at max, how much can this, like at minimum, how much minimum can it go? How much negative can it go? The amount of negative it can go is minus 180, right? Minus 180 it can go. And like how much least negative can it go? I mean, like, yeah, how much maximum can it get? Like if omega equals 0, it goes to minus 90. So what is my angle range basically? So if I write this as like theta, and this is g of g omega, this, right, these things like help us to plot the graph basically. H of g omega. Okay, like you might say, why are we plotting? Is it like in gate do you have to plot? Like sometimes you have to approximate it or find like some parameters. So obviously these things, right, will help. So my theta, right, what is my range of theta? So my range of theta is between minus 90 to minus of 180 degrees, right? So my range of theta is between minus 90 to minus 180 degree. So like again, right, let's do the table, and again, right, I will choose the third point as 1 by tau. Okay, because this will get cancelled and I will be remained with 1 only. So omega is 0, and what is my magnitude of this omega? So magnitude is, like, if I put omega, okay, I will first write the 3 points, 1 by tau, and this is infinity. Okay, so what is my magnitude of g omega? So if I put omega equals to 0, what is it? This is finite, this is fine, this is finite, right? This becomes 1 plus 0, that is fine, this becomes 1. But what about my this becomes 1 by 0. Okay, so what do I get? I get infinity itself, right? So this will be infinity. And what about this one? If I put 1 by tau here, okay, then this will be under root 2, right? And 1 by tau, so this will be tau by under root 2. Okay, so do it for yourself. I'm doing it just a bit fast, you solve it slow. So it is tau by under root 2, or we can write 0.707 tau. Okay, and what about infinity? So what infinity, right? If you put omega equals to infinity, so this is again infinite and infinite, and this is finite, so 1 by infinity is 0 itself, right? So this will be 0, right? What about here, right? If I put omega equals to 0 here, as I told right earlier, this will vanish, right? And this will be remain, and this is minus 90 itself. So this is minus 90. And if I put omega goes to 1 by tau here, right? So this is tan inverse 1, which is 45. Minus 90 minus 45 is minus 135. As I told, right, it is reducing. From minus 90, it is reducing. Minus 135. And if I put omega equals to infinity here, right? Infinity if I put, so this whole thing, right, becomes 90. So minus 90 is minus 180. So it is minus 180 degrees, right? So this is what this is, angle of g of j omega. So how we will plot it? Okay, how we'll plot it? So what is happening is that at omega equals to 0, like as my omega is really small, right, as my omega is getting really small, this is tending towards infinity, this is tending towards infinity, and my angle is minus 90. So my angle is almost minus 90, and this is tending towards infinity. So this, right, if omega is very small, right, this will follow like this one only, like this one. Where did it go? Yeah, like this one. So it will be like asymptote itself, right? It will be like asymptote. So for omega, very small values of omega, what will happen? It will follow like this one. Okay, this one. It will have a real component with it, right? So if you do it like that one, it will have a real component for it, but the real component will be very less. You try to solve it using that like imaginary real component method, right? And what you will see is, for omega, very lower values of omega, the real component will be very low and the imaginary component will be very high. From the angle itself, we can understand. Whenever the angle is very like 90 degrees, right, then the imaginary component is dominating basically. So very close to minus 90 or minus 270 or like plus 90, then the imaginary component is dominating. So if my like what I was saying, yeah, so my imaginary component will dominate. So I will start off something like this, right? It will have some real component, but it will be very less. Then slowly what happen, the real component will also increase. Okay, real component will also increase, and from the angle itself, what you can understand, I'm starting with minus 90. Okay, this is minus 90. Then slowly my angle is reducing further, so I will go in this direction and not in this direction, because if I went in this direction, then my angle should increase, but I'm going in this direction, hence my angle is reducing, right? Angle is reducing. So I will go in this direction. Okay, and slowly what will happen towards the end, right? Towards the end, I will try to finish in this origin itself, because my magnitude is reducing. Okay, my magnitude is reducing. So here, right, you can see from infinity magnitude it is going to finite, then going to 0. So my magnitude is also reducing. Here, right, magnitude is very high, almost infinity, right, almost infinity. Here it is reducing. Here the real component will slightly increase. Why? If you do it using that method, right, I will give you the homework and I will try to write the notes here, right, of the real and imaginary components, and if you check it, right, so you will understand that here why the shape is like this one. Okay, and this point, right, this point is 45 itself, minus 45 basically. Okay, or you can say minus 135 from the real axis, right? So yeah, the magnitude of this one is 0.707 tau. Okay, so yeah, this one is this one. Okay, so this will be basically polar part. So this part, right, this part is similar to the question 1 and this part is similar to the question 2. Okay, so if you get this circle structure, why? Like I've already done the imaginary and real part of that one, so from there also you can understand why is this like a circle one, right? Okay, and why is this like a straight line one? Okay, from the question 1, and this is from the question 2. So question 2, question 1. Okay, so yeah, that's why we did all those first, then we came here, right? So what I am doing is giving you a bit of homeworks, right? Giving you a bit of homeworks. So all this you try to solve, and in the next lecture we'll start off with this one. So like what I will do is I will try to solve this first one. Okay, try to solve this first one. You also try it right now, and the other two, right, we'll solve it in the next lecture. I just want to say you few observations and key points, right? So like let's do this one. Okay, let's do this one. So let me copy this one. Let me copy this one, right? So if I copy this one, what do you see? And this is equals to, like I will replace s equals to j omega, again the same method, right? So yeah, and what is this magnitude? like now I will plot the magnitude and the phase angle basically, right? So magnitude will be something like this. I'm doing this directly now. It is 1 plus omega tau 1 whole square and what is my angle basically? My angle, right? Obviously the numerator has 0 contribution, but this has 2 angle contributions, right? So 0 minus so writing this directly now, so this will be simply minus only. 0 I can remove, right? And this bracket also, okay, bracket also I can remove. This, all this will be minus only. So what is the minimum angle here? So if I write this one as theta, right? Theta, if I write this one as, what is the range of my theta? So theta, right? If I put omega equals to 0, what do I see? Always put the critical points, right? So if my omega equals to 0, this becomes 0, right? And if my omega is infinity, this becomes 90, this becomes 90, and plus minus 180. So my theta is varying from 0 to minus 180 itself, right? So it will go from positive real axis to negative real axis, okay? But how will it vary? How will it vary? So we have to see that one basically, okay? So obviously we won't be able to plot it totally accurately, sorry for the word pen, but there we'll try to approximate it, okay? So if I make, like, you do, what is your homework? You try to do it using the method 1 also, right? Using the imaginary and the real part, okay? So here, right, if I put omega equals 0, what is my magnitude? Omega equals 0, then this time, right, I'm not getting infinite magnitude, I'm getting finite magnitude. So this is 1 1, okay, this becomes 0 0, so it is 1 itself, right? So again, right, let me write down the critical points. 0, I will again do it for 1 by this time, right? What I will assume is, I will assume that tau 1, for our simplicity, tau 1 equals to tau 2 equals to tau itself, okay, for our simplicity, okay? So if tau 1 equals to tau, so I will take another point as 1 by tau, right? Omega equals to 1 by tau, okay? And what about another point? Omega equals to infinity, omega equals to infinity. So if omega is equals to infinity, then what do I see? What do I see? So like, what is the magnitude? Sorry, if omega is 0, what is the magnitude? It is 1 itself, right? As discussed earlier. So it will be 1 itself. And if it is 1 by tau, so tau 1 equals to tau 2 itself. So this becomes 1, this becomes 1. 1 plus 1 is 2. 1 by under, like, under 2 into under 2, it is 2 itself. So it is 1 by 2. So hence I get 0.5 here. And what about my omega equals to infinity? So my omega is equals to infinity. So what is happening? Like, this is very high, right? I can ignore this one, I can ignore this one. This is simply 1 by infinity itself. So it is going to 0 itself. So what I can observe is my magnitude is reducing and my angle is also reducing, right? In the negative direction it is increasing, my angle, that is. So this angle of g omega, basically if I put omega equals 0, I say 0 degree angle. Already we have already done the critical points, right? So this is 0 degree angle, this is minus 180 degree angle, right? Minus 180 plus 180 doesn't matter, you are adding 360 or something like that. But here it is interesting, what is happening at 1 by tau. So at 1 by tau, if tau 1 equals tau 2, so this is tan inverse 1 and this is also tan inverse 1 itself. So like this minus this is 45 and this is 45, so minus 45 minus 45, it is minus 90 itself, minus 90 itself, right? So yeah, this is one, okay? So yeah, now, right, from where I am starting, I'm starting from 1, right? Magnitude 1 and angle 0. So I'm starting at the real axis with magnitude 1 itself, right? Okay. Now from like again what is happening now, my angle is reducing, right? My angle is reducing and my magnitude is also reducing, right? So obviously it won't remain one, it will be something like this, something like this, something like this. Magnitude will keep on reducing and I'm crossing this axis, right? Again reduce and it will go to 0 here because I'm going to origin at minus 180. So it will keep on reducing and it will go to 0 here. So this time, right, it won't be like a circle itself, right? It won't be like a circle itself. So it will be something like this. Okay, this became triangular, which is difficult. I don't want it to become triangular. Yeah, it will be something like this, right? So if I make it, yeah, even further like this one, right, it was something like this. Here what you can see here, the magnitude is 1, it is reducing. Angle is also reducing, right? In the negative direction it is increasing, reducing. Okay, so yeah, my plot will look something like this. Obviously if you plot it in the computer or in the MATLAB, exactly this one will be like this, right? But this is a good approximation basically, and that is all we need, right? And few critical points we need that we'll understand when we solve the question. So this is right, this is omega equals to 0, this omega equals to infinity, right? This omega equals to infinity. Okay, so yeah, this one, right? And now like let's understand few things. So my plot is going from here to here, right? From here to here it is going. Now I'm giving you a few terminologies to further better understand this topic. So what is my head? Head is the end of the polar plot. This is a terminology. This is nothing like any concept or something. This is just a terminology, right? So head is the end of polar plot. So wherever my polar plot is finishing, basically at omega equals to infinity, okay, that point is known as the head. So this is the head of the polar plot. And what is tail? Tail is the start of the polar plot, right? Basically at omega equals to 0. So here, right, from wherever I am starting is known as the tail, and from wherever I am ending is known as the head. Just like this one, right? My head and my tail. Okay. So if you don't like, this is just terminology. This is nothing fixed or something like that, right? So why did I tell you about this one? So when a pole at the origin is added, right, the head and the tail of the polar plot is shifted by minus 90 degrees in the clockwise direction. Okay. So like if you see, right, if you see that if a pole at the origin is added, then what is happening here, right? Here both poles are like at the real axis itself. Okay, but here if you see, like in the previous example, right, here, right, I had simply pole at the real axis. Now what did I do? I added a pole at the origin. This is the pole at the origin, right? Like s equals to 0 is a pole, right? And this is at the origin. So if I add a pole at the origin, my head and tail both are shifted by 90 degrees, minus 90 degrees this time basically in the clockwise, sorry, or you can say 90 degrees in the clockwise direction. Okay, so previously like this one was here, okay, this tail was here, but now my tail is here, right? This is on the minus 90 degree angle, and here, right, my head, okay, my head was, okay, this is very interesting, my head was at minus 90 degree angle. So this is like minus 90 degree, this is not 0 degree. Okay, try to understand, this is not 0 degree angle. Okay, this is, just be very careful. 0 degree angle is this one. Okay, it is starting from 0 degree angle, but it is going negative, and it is ending like this one, right? So this is minus 90 degree angle, this is not 0 degree, even though in the graphs, in the plots also you can see that this is like ending in the origin, this will be 0. No, this is not 0 degree, right? So my angle is increasing. So like the plot, right, the perfect plot will be something like this. Yeah, this like this. Okay, like this itself. Okay, so this is not 0 degree, this is 90 degree. So like this, I don't know if it will be a circle or not. I have to check for it if it will be a circle or not. You guys check, right? Plot the imaginary and the real, and from there, if it follows the locus diagram of a circle, then it will be a circle. Okay, but I don't think this will be a circle. So this will follow like this one, right? So I hope you get it, right? So this is ending towards minus 90, not 0 degree. Okay, so yeah, this is minus 90, and I am further shifting it to 90 degrees, the head, that is. Okay, so both the head and the tail are shifted by 90 degrees in the clockwise direction if a pole at the origin is added. Now if a pole at the real axis is added, right? If a pole at the real axis is added, then the head of the polar plot is shifted by 90 degrees in the clockwise direction and the tail remains same. Why in the clockwise? Because it is in a denominator and we are subtracting the angle, and if we subtract, right, it goes in the clockwise. I hope you understand. So like head of the polar plot is shifted by minus 90 degrees and the tail remains same. And why is this is the case? Basically, if we have added a pole in the real axis, right, then we have some real component, right? Like here we have some real component. So even though like at omega equals to 0, this doesn't contribute to any angle, right? Omega 0, we have only plus 1 and this is 0 degree. So this doesn't contribute to any angle, but at omega goes to infinity, this contributes to 90 degree basically. So here, right, at omega equals 0, it doesn't contribute to any angle, hence the tail remains same because tail is related with omega equals to 0, but head, right, it shifts because it is related with omega equals to infinity. So here if you see, like my tail is remaining same, right? Tail is remaining same, like this one. If you compare it to this one, right, my tail is remaining same. I just added a pole, okay, in the real axis, right? Okay, where is this? This is the transformation. I just added a pole on the real axis, right? And this is the same. So if I add a pole on the real axis, then what is happening? My tail is remaining same, but my head is getting shifted, right? Head has shifted to minus 180, as you can see, right? So this will be something like this. Let me, yeah, this will be something like this. This will further go to minus 180, right? Okay. So obviously I'm just doing this all this approximately to better visualize what is happening, right? This is going towards minus 180. No, this is not 0. It's not like, yes, this is going to origin, but the angle is not 0 here, right? Angle is minus 180. Please be careful of that. Please be mindful of that. It is ending to minus 180, right? Minus 180. Like here, it is ending to, where did it go? Here, right, it's ending to minus 90, not 0 degree, right? So these things you have to keep in mind. Okay, we'll do more examples from there, we'll understand. So the ending is very important. Try to understand this is going to minus 180. What is the angle of this one? The angle of this one is minus 180. With the real axis, the angle of this one is minus 180. With the real axis, what is the angle? Is minus 90, right? The real axis, what is the angle? The angle is again minus 180, like towards the ending, right? So like these are the 2 points that you need to keep in mind. Like when does the head shift, when does the pole shift? So head is related with omega equals to infinity and tail is related with omega equals 0. Okay, all these things I hope you understand, right? So what is the and the observation? Okay, these are the few observations, right? If my OL tip is a minimum phase system, then the tail of the polar plot will represent the type and the head of the polar plot will represent the order of the system. Now what is minimum phase system? Now many people define minimum phase system like differently, but general rule of thumb is for minimum phase system, right, all the poles and the zeros of the transfer function should lie on the left hand side of the should lie on the left hand side of the S-plane, right? Yeah. Minimum phase systems. What does minimum phase system mean? All the poles and lie in the S-plane. Okay, so this is what my minimum phase system is. Like if my system, right, it is non-minimum phase system, then the angle calculations will be different. Why? Because it will lie on some other quadrant again, right? The angle will be different for other quadrants, as I told you, mentioned in the angle calculation also. Try to remember it, right? So yeah, if it is a minimum phase system, basically if it is a stable system and all the poles and zeros are on the left hand side of the S-plane, then the polar plot will represent the like the head of the polar part will represent the order, and the type will be represented by the what do you say, by the tail, right? Why? Because what is type? Type is basically number of poles at the origin, and basically that is what tail represents, right? It is basically the behavior at of the angle at omega 0. It is the start of the polar part. So whatever, like if it is starting from angle 0, right? If it's starting from angle 0, then my type is 0. If it's starting from angle 90, then my type is 1, because it has one pole at the origin. Okay, one pole at the origin. If my angle is minus 180, then it has type 2, right? Type 2, it has two poles at the origin, right? So now what about head? Head is about the finishing, right? Head is about the finishing. So what about my head? So at omega goes to infinity, wherever I am finishing, right, that will be the order, right? So that amount, that will be the number of poles I will have in the denominator, basically. Okay, that will be number of poles I have in the denominator. Okay, so yeah, that is one thing. But like one more thing, okay, I think the head part is a bit wrong, because like even if we have some zeros, right, if we have some zeros, then this won't be like correct. So head part I will remove, because at omega goes to infinity, right, the zero part is also coming. Okay, that I didn't thought about. Okay, that I didn't thought about. So yeah, so I will remove the zero part actually. Okay, I will explain it in the next video if some doubt comes. So head, right, head I can write, head I can write, because like let's say what this meant was, like if I have, let's see, if I have s plus 1 by s plus 2 into s plus 3. Okay, now if you do omega goes to infinity, what is the angle? Angle is basically minus 90, right? Now if I don't have this 0, right, simply s plus 2 into s plus 3. What is omega goes to infinity angle? It is minus 180. So yeah, I can't tell the order from head, right? I can't tell the order from head if I have 0, right? So I'll just simply remove this head, but type I can tell. Type I can tell, because at s equals 0, even if there is 0, that will contribute 0 degree angle, so it won't make any difference, right? So I will just remove the head from here. The statement is a bit wrong. Okay, but type will definitely represent the the tail will definitely represent the type of the polar part. So like what I can say is, I can write here, right, if the what I can write, if angle of g of j omega, h of j omega, right, at omega equals to 0, equals to 0 degrees, right, equals to 0 degrees, then what does this mean? This means this is a type 0 system. This is a type 0 system. Okay, now I will just copy this one and write it here. But like what will happen is, like for more than that pole, right, then we can define the angle. Okay, so this is between 0 to 360. Okay, that thing also you have to understand, that my theta, right, like these, all these are conditional. Okay, this is just to give you a brief idea, like you can't generalize this one. So theta should lie between 0 to 360, right, then only we can define this one, right? Like let's say if I have 5 poles, right, 5 poles at the origin, type 5 system, even though that won't happen, if I have 5 poles at the origin, what is happening? Then my angle, it will become basically minus 90, right, minus 90. But that will say it is type 1 system. So yeah, that's why I wrote it with a condition, right, condition, because you may get confused. So okay, can I copy another one, right? So if my angle is 90, if my angle is, okay, this is not 90, this is minus 90 basically. One, two, three. Okay, 4 for type 4 I can't explain, right? If it is 360, then it can be 0 degree also, this can be type 0 also. So yeah, that is but difficult to predict, but all these things we can predict, right? Up until type 0 to 3 we can predict, right? Type 0 to 3 we can predict. Okay, that's why I made a condition over here. So basically, what did you learn in this lecture? Basically, we learned how to plot the polar plot, how to find the angle and the phase, right? Sorry, how to find the magnitude and the angle, and what is the ending, what is the starting, how to find this angle. So do try to understand. This is minus 90. Okay, this is minus 90. Okay, so like the angle is from positive real axis, right? Angle is from positive real axis. Okay, so this is ending towards minus 90 itself, right? Minus 90 itself. So if this is a circle or not, that we have to check with the imaginary and the real components. Okay, you try to do it. That is the homework for you. Okay, so yeah, that is it for this lecture. We also understood that if we add a pole at the origin, basically if you increase the type, then what happens to the head and tail? If you add a like a what do you say, if I had a pole at the real axis, then what happens, right? All these things we did. Okay, so I gave you a few homeworks, right? Try to remember, these are the homeworks. Try to plot this, right? Try to approximate these things. Okay, and in the next lecture we'll restart from here, and also do few more polar plots, right? Yeah, thank you for watching.